Hi everyone, welcome back to our channel. In today's tutorial, we are going to learn something about called HyDE RAG. HyDE stands for Hypothetical Document Embeddings. If you have seen our earlier tutorials on RAG, we followed something very basic and fundamental framework, which is also sometimes called as vanilla RAG. So here in vanilla RAG, we does things in this sequence actually. So this is the original query that we get from the user. We embed that into a numerical vector using an embedding model, and after that we use a retriever function to extract some top relevant chunks from our vector database. And once we retrieve those chunks, we combine them with the original query and we send them to the LLM, and LLM gives us the final answer. That's it. This is the fundamental sequence of tasks that we use in this vanilla RAG. The fundamental problem with vanilla RAG is, so in many a times the user queries are short, sometimes vague, and sometimes written in a very different language than what is used in the original document chunks actually. For example, here, for example, say when a user asks about pin's stability issues, the embedding is sparse and may not match any chunk phrased like this one's actually training instability. So if the document chunks contains this kind of wording, and if a user sends this kind of wording, so match between these two is very difficult actually. So the retriever fails to retrieve appropriate chunks that are more closer to the query. So we get some garbage output actually. In order to address this drawback, LLM researchers developed a method called HyDE, and it directly solves the problem. Here it works in a very simple way. Here is the sequence of tasks that we do in HyDE. Here, instead of directly embedding the raw query and send it to the retriever, we ask the LLM to generate a hypothetical answer. This hypothetical answer does not have to be correct. It only needs to look like a real passage from the knowledge base. For example, if the question is like how is incompressibility enforced in pins? So the hypothetical answer that LLM generated may look like this actually. In physics informed neural networks for incompressible flow and so on so on. So here, if we look at here, it captured the main incompressibility here and pins. Here we have given this acronym, and here the LLM generated its full form. So basically it increases the accuracy and gets more relevant chunks for the given query. This passage is semantically dense and written in the same style as the documents. When we embed this, it sits much closer to the actual relevant chunks in the corpus, which makes retrieval more accurate. Okay, and here, if you look at the sequence of tasks, so these are the things that we do actually. We take the original query, we ask the LLM to generate a hypothetical answer, and we embed the answer into some numerical vector, and we use that hypothetical answer to retrieve these chunks, and then we combine the retrieved chunks with this original query to form the final prompt, and we ask the LLM to generate the final answer. So that's it. Here the role of hypothetical answer is to just retrieve the most relevant chunks for the given query. That's it. So the only change is one extra step at the start, but this small change improves the retrieval dynamically. The main reason why this HyDE RAG works is because instead of comparing a sparse query against long document paragraphs, we compare a passage with passage, the hypothetical answer against the chunks. That's a much fairer comparison, and it consistently pulls more relevant chunks actually. And the final answer generated will have fewer hallucinations. So in this tutorial, we are going to implement this HyDE RAG pipeline from scratch. So let's get started with the setup and imports. So here in this section, we are going to import some basic libraries that we will be using. So here are some basic libraries, and here is our main sentence transformer library. So we use Hugging Face transformers to get the embedding model, and here PyMU PDF library for reading this PDFs, and FAISS for vector search, and NumPy for basic mathematical operations. So here we are setting up our basic information like the corpus directory. So here is our corpus directory. So here we have this data within that raw PDFs, and within that I have all the PDFs that I'll be using in this tutorial. So here are some 6 research papers on physics informed neural networks. Okay, and the embedding model that we are going to use is all mini LM L6v2, and I'm using this top k as a default value to 5 to tell these many maximum chunks that retriever has to identify actually. So it can identify any number of chunks, but we are only interested in the top 5 chunks. And this is the maximum number of chunk tokens. Here I am putting as 400, but you can increase actually. And the open router model that we are using is OpenAI's GPT-5 nano model. So if you have any other thing, just change it actually. So here I am setting the open router API key. So I put that key in my environmental variables. So I'm just using this os.getEnv to get that key actually. Once we import the libraries and set up our configuration, next is to load the PDF files into our notebook and do the chunking operation. So here I have written two functions, read PDF and read text, to read the text and to read the PDFs and extract the contents inside of it. And after that, here I have two main functions. So this is a load corpus text functions and another one is a simple chunk function. So here it combines the text that is extracted from this raw text and raw PDF. So these two functions are called from this function. So here is our read text, here is our read PDF. So it will build the entire a big corpus actually, meaning it combines all the data that was generated from each PDF. So it puts into one single big chunk of document. And here in this simple chunks function, we take the entire combined information, we chunk it into smaller chunks. So here is our main build corpus function. This corpus function contains calls to the load corpus, and here we have this simple chunks function. So we call these two functions from here actually. So we are sending this corpus directory path, and it generates the complete raw docs, and it generates the simple chunks using this simple chunks function. Okay, if you look at here, all our PDFs, 6 PDFs combinedly was divided into 135 chunks. And after this chunking operation, we are going to develop embeddings and FAISS vector index. So here I'm just loading this embedding model from the sentence transformer and storing it into this EMB model. So here we take all chunks we just created and then turn them into embeddings using our sentence transformer model. Once we have these embeddings in place, we push them into a FAISS index. FAISS gives us a fast similarity set. So even if we have thousands of chunks, retrieval happens in milliseconds. So at this point, we now have a searchable vector index. So if you look at here, we have 135 vectors and each vector is of 384 dimensions. And if you look at here, we have 135 chunks. It means each chunk is properly embedded into a vector of 384 dimensions. Okay. And next, after we develop this FAISS index, here we are defining this retrieve function. This retrieve function does a very simple thing actually. So given a query, it will embed the query and then search the FAISS index to return the top k most relevant chunks from all the chunks. Here, each hit, meaning each chunk, comes back with the text, its document source, and the similarity score. So this will be the very foundation of our HyDE pipeline. This is a very central function in this entire RAG pipeline actually. Be it vanilla RAG or be it HyDE RAG, this retrieval is a very fundamental step. And here we are defining our LLM helper. So, okay, here we write a small wrapper for calling the LLM model through Open Router API. We send a prompt to this function, and this function generates a response, and the response is mostly in the form of a text that the LLM returns actually. All our model calls, whether for generating hypothetical answers or for producing the final answer, will go through this helper function. So that's it. Up to here we have created all the utilities that we need actually. Next, we are going to write our HyDE specific code. So this is our first HyDE code. So here we are generating this hypothetical answer. So here we take the original question and combined with some instructions, and we use this LLM model to generate a hypothetical answer actually. So here we are sending some prompt like this. So here we are asking it to write a concise factual looking answer to the user's question below. This one, this is our original question, and this HyDE generate function uses this instructions combined with this question, generates a response, and this HyDE generate function returns that response. After that, here we are writing some formatting function. So what it basically does is we get the chunks, right? So it basically formats the chunks with appropriate references. So for example, if you look at our final answer, so this is our response, and if you see this kind of citations everywhere, here, here, Okay, this is the context that we want actually to verify whether the answer is correct or not, to verify whether it is coming from the retrieved documents or not. So that's why we are formatting our retrieved chunks with this kind of references indexing with the chunk IDs actually. That is the formatting that we are doing. And after that, here we are preparing our answer prompt. So this is our basic answer prompt. If you look at here, we use the hypothetical answer mainly for optimizing the retrieval process, if increasing the efficiency of the retrieval process. Once we got the chunks from the hypothetical answer, so we just leave that hypothetical answer there itself. We use the original query afterwards. Okay, here we combine the retrieved chunks with this original question and creates this entire combination of query and context. Here context represents the chunks, and here we combine some instructions. Okay, and we send this answer prompt to the LLM through this actually after formatting. After formatting means we prepare the context with appropriate citations so that LLM returns the answer with some citations actually, the citations from the references that we send through the context. Okay, this is our final LLM answer function. We combined all of our HyDE RAG functions in this pipeline. So this pipeline fundamentally involves three steps. The first one is generating the hypothetical answer. Once we get the hypothetical answer, we use the hypothetical answer to retrieve the hits, and hits means the top k chunks. So once we get the chunks, we combine these chunks with our original query and generates the final answer, and this final answer along with some information will be returned from this function. This is our main HyDE RAG pipeline. After we create this pipeline, let's see how to call it actually. So here we have written a small query. For example, in pins, how is a divergence free constraint typically enforced in incompressible flow problems? This is our original query. So here we are calling this a HyDE RAG function to generate the response. So for this we are sending this query and top k. Here in the beginning, top k is the maximum number of chunks. So I have defined it as 5, but you can increase it based on your answer quality. You can increase more or less, that depends on you and the total number of context length that your LLM model can support. Once this response is retrieved, here I am printing the information like the original query, the hypothetical answer, and the retrieved snippets, and the final answer. So if you look at it here, so this is our hypothetical answer actually. In pins, the incompressible flow, the divergence is usually enforced in two ways. This is a hypothetical answer, okay? And we use this hypothetical answer to retrieve these chunks. So these are all the retrieved snippets that are close with this hypothetical answer. Okay, after we get this snippets, so these I have just written as the snippet IDs, but we get the original chunks actually that we can print if you want. So here you can print it. So I just printed the document IDs and the chunk numbers, but for LLM we are sending the main content of each chunk along with this original query as you see here, and this is the final answer that we get from the LLM with citations. That's it. This is the overall workflow of this HyDE RAG. Now that we have seen the entire HyDE RAG pipeline in action, the key takeaway is simple. By adding this one extra step, that is generating a hypothetical answer before the retrieval, we makes the whole system much more accurate and reliable. Instead of comparing a short query against some long passages, we compare passage with passage. That makes retrieval process more fairer and more effective. But of course, it adds some small extra cost and latency because of that one extra call to LLM to generate the hypothetical answer. But the overall improvement in recall and the grounding that we get in the final response makes it worth. Especially, this is very much useful in technical and research heavy domains. This entire implementation is completely done from scratch using plain Python and some simple Python libraries. So you have full control and you can extend it however you like. You can swap in some bigger models. Instead of here I used all mini LML6v2, right? You can try something else, just change this EMB model name and accordingly change this sentence transformer. If you are using a sentence transformer model, then that's fine. If you are using any other library model, then you have to use that library here, and you can definitely change this model to any model. So Open Router has a plethora of models, or if you want, you can plug this entire HyDE RAG pipeline in some large agentic framework. So that's all. You can do anything you want with this HyDE framework. That's it for this tutorial. If you found this tutorial useful, make sure to like the video, subscribe to the channel, and let me know in the comments about what other RAG variations or AI pipelines you would like me to cover next. See you in the next tutorial. Thanks for watching. Happy learning.